Okay, so we are now going to start the sixth chapter, and this involves the notion of isomorphism of groups. So in this first exercise, we have to find an isomorphism from the group of integers under addition to the group of even integers under addition. So let us first denote these groups by some symbol. Let Z and 2Z denote the group of integers under addition and its subgroup consisting of all the even integers respectively. Now since this we are stating that this is a subgroup of this, so automatically this is also a group under addition. Okay, now we have to produce we have to define an isomorphism. So what can be more natural than this function? Define f from z to 2z by f of n equal to 2n. Now clearly this is a well-defined function. For every integer n, its double is again an integer and it's a unique integer for this given n. Clearly f is well defined. For two distinct integers n and m, we have two n also distinct from 2m, because otherwise n has to be equal to n has to be equal to m, i.e. f of n is not equal to f of m. So this proves that f is 1 to 1. Hence f is one to one. Next, for any element say x belonging to the set of all even integers, we have x equal to 2k for some integer k, because that's how every even integer looks. But then x is equal to f of k, hence f is onto. So we have proved that f is a bijection between these two sets. Also, for any integers I and j, we have, so now whatever we now have to verify, what else we are left to verify is that condition. What is f of I plus j? And I write I plus j here because the binary operation is addition of integers. By definition of our function, this is 2 times I plus j, but we already know that multiplication of integers distributes itself over addition of integers. So this is 2i plus 2j. Now 2i is f of I and 2j is f of j. So now we can conclude that hence f is an isomorphism. Thus f is an isomorphism of Z onto 2Z, and that is why those two groups are isomorphic to each other. So that's the solution. Next, the second exercise. Find this, the automorphism group of the group of integers under addition. In other words, we have to find all the automorphisms of the additive group of integers. Okay, so let's see. Let f be any element. In other words, f is an automorphism of Z or Z. Since f is, okay, now there is a fact about such a function. Should I prove that? Okay, let me just prove that one first, because that is something we are going to use. We claim that f of n is equal to n times f of 1 for all integers n. Okay. Now, since f is an automorphism. So we already know some things, right? We know that f of 0 is equal to 0. In fact, for any isomorphism, this is the case. If you evaluate the isomorphism at the identity element of the group, then you get the identity element of that other group. In this case, both the groups are the equal, they are the additive group of integers. So f of 0 must be equal to 0. Regardless of what the function f is, this has to be the case. But then this is just simply 0 times f of 1. We don't really know what f of 1 is, but whatever it is equal to 0 times f of a1, because after all this will also be 0. So you can see that this claim is true for n equal to 0. Now suppose that f of n is equal to n times f of 1 for some non-negative integer, for some integer n greater than or equal to 0. Then what about f of n plus 1? Because f is an isomorphism, so f respects the binary operation. So from that property, this will be f of n plus f of 1. So this just comes from the fact that f is an automorphism, and hence an isomorphism. But now our supposition allows us to write in place of f of n times f of 1 plus another f of 1 we have already. So taking that f of 1 common out, we have this. Hence, by induction, we have this for all non-negative integers. But we claim more, no? We have claimed more. We have claimed that this is also true for negative integers as well. Now, if n is a negative integer, then minus n is a positive integer, and so by what we have proved above, f of minus n should be equal to minus n times f of 1. So that means we are applying the already proved case, that is this case, to the positive integer minus n. But since f is an automorphism, so f of minus n is equal to minus f of n. This is the property of automorphism, in fact any isomorphism. But since f is an automorphism f of minus n is equal to minus f of n. Hence, so you substitute that here, so you would get minus of f of n is equal to minus n times f of 1, or now multiplying on both sides by minus 1, we get this. So that means even when n is a negative integer, our claim still holds. Thus, or we can write like this, this proves our claim. This proves our claim. Okay, so now we know this fact about f, that if we evaluate f at any integer n, then that equals n times the value of f at 1. We are now going to use it. Now, since f is an automorphism, it's an onto function. Naturally, it's one-to-one also, but we are going to use the onto-ness now. Since f is onto, so 1 is an output of f for some input. 1 is equal to f of m for some integer n. So by what we have just now proved, that is our claim. Thus, our claim above now gives us what? 1 equal to f of m, but that is m times f of 1. Now m is already an integer, and f of 1, whatever it is, depending on f, is after all an integer. So that means the product of two integers is 1. This implies that either both of them are equal to 1 or both of them are equal to minus 1. These are the only two possibilities. So we have two possibilities, and corresponding to each possibility we will have one automorphism, and we will now see that because of this there are only two automorphisms. If f of, we are of course going to focus on this, what f of 1 is. If f of 1 is equal to 1, then by our claim f of k, if we want you can write n here also, then f of k is equal to k times f of 1, but now since f of 1 is 1, so this just becomes k. For all integers k. On the other hand, if f of 1 is equal to minus 1, then again by our claim, this is minus k. For all integers k, both of these functions or mappings are automorphisms of our group. Now you please verify this. Okay. So that means these are the only two automorphisms, and as such the automorphism group of the additive group of integers has only two elements. It is a two-element group. Just recall, now before you verify this, just recall what is it that you have to do. Say you want to show that this second function is an automorphism. You have to prove three things. The first is that this function is one-to-one, and the second thing is that it is onto, and the third one is that it satisfies that condition, that it should respect the binary operation. So that part you please verify. So you now know what the automorphism group of the group of integers under addition is. It has precisely these two automorphisms. And this in fact is a special case of a somewhat general result. This is the case with any infinite cyclic group. In any infinite cyclic group, there are precisely two automorphisms. But anyway, let's just now see what comes next. Let R class, R positive, be the group with a group of positive real numbers under multiplication. Under multiplication. Show that the mapping phi of x equal to square root of x is an automorphism. Of this group. Okay, so now we have the multiplicative group of all positive real numbers, and this function maps each such number onto its square root, which we know from analysis exists. So we just simply start by writing clearly phi is well defined. This may look somewhat dumb, foolish. You may not even be concerned about this type of issues, but always keep in mind when you are looking at a function that has been defined, always make sure that it is well defined and make sure that you know why it is well defined. You may choose to not even write this line, but you yourself should know why this is well defined. The reason is that if we are given any positive real number, that means any x from here, then from real analysis we know that it has a positive square root, which is a positive real number itself whose square is equal to the given real number. It exists and it is unique, and that is why phi is well defined. For any two positive real numbers, if we have this, then obviously if you take squares on both sides, you get x equal to y. That means if the outputs are equal, then the inputs are also equal. So that means our function phi is 1 to 1, it is injective. Next, ontoness. For any z belonging to R class, we have its square belonging to R plus. That's because if you take the square of a positive real number that is also a positive real number, such that phi of this is equal to this, which is equal to z. Hence phi is onto. Note one thing, that when you see something like this, do not just simply write z. In general, if nothing is mentioned about the sign of z, you only know that z is a real number, then this is true. Why? That is because, what is the meaning of this symbol? This symbol represents a non-negative real number whose square is z square. For example, if you take this, say, you do not remove the square and the radical sign and simply write minus. This is wrong, because by definition this is a non-negative real number whose square is equal to minus 1 whole square, and such a number is not minus 1 because it has to be non-negative, but such a number is 1, and the reason for that is this: minus 1 is a real number whose square is equal to minus 1 square, but 1 is also a real number whose square is equal to minus 1 square, and among these two numbers, one is non-negative. So that's why we have +1, or in other words, this. Okay. So now pi is onto. So what is left for us to do? Namely, we have to verify that condition. Also, for say A and B belonging to this, we have phi of AB. Why do we take AB here? That's because our binary operation is multiplication of real numbers, not addition. But we already know from elementary properties of radicals that this is equal to square root of A times square root of B. So that's it. Now we are done. Hence, phi is an automorphism of the multiplicative group of positive real numbers, and this completes the solution. Next, show that the group U8 of the, you already know what this group is, but still let me just once more say what it is. It consists of all the positive integers less than 8 and relatively prime to 8, and the binary operation is multiplication modulo 8. This group is not isomorphic to U10, the similar other group where the modulus is 10. Now we have to go back to an example where we discussed some aspects of this group, and that example is this. We have, or we know from example 4 of chapter 4, I think, yes. That one of these two groups is cyclic, but the other one is not. U10 is cyclic, I think, but U8 is not. Yes. But U8 is not. So they cannot be isomorphic to each other. The reason is this result theorem 6.3. Because that theorem of course has some subdivisions. In one of them, the statement is just this: if you have two groups G and G bar and there is an isomorphism of G onto G bar, then if G is cyclic, then G bar also has to be cyclic. So because of that, and because of the fact that this is not cyclic but this one is, so they can never be isomorphic. There can be no such isomorphism. So that is the solution. That means they are really distinct as groups. They are not the same group disguised in different forms. That's not the case here. They are actually group theoretically also they are distinct. Next, show that U8 is group theoretically distinct from U10, but it is group theoretically the same as U12. Show that U8 is isomorphic to U12. So that means here we have to produce an isomorphism, an actual concrete isomorphism. Okay, so in the solution we just do that. Define a function f from U8. So let me just write the elements also here. The elements in U8 are these integers 1, 3, 5, 7, all the positive integers less than 8 and relatively prime to 8. And the similar one for 12 is 1, 2, 3, 4, 5, 6, 7, 11. By these formulas, f of 1 is defined to be equal to 1, then f of 3 is defined to be equal to, that is, we just maintain the order and define the function like that. So f of 1 is 1, f of 3 will be 5, f of 5 will be 7 and f of 7 will be 11. Clearly, f is well defined. Of course, we can just see that both the sets are small and the entire thing is given, is well defined and also bijective, 1 to 1 and onto. So to prove that this is an isomorphism, we just have to verify that condition, that it respects the binary operations. Now, what are the products that we need to check, need to verify? We now verify that f of AB is equal to f of A times f of B for all elements A and B in U8. Now, how can we reduce our labor? Note that since U8 and U12 are both abelian is written like this in this book, are abelian, the equation f of AB equal to f of A f of B implies f of BA equal to f of B f of A for all A and B belonging to U8. And this helps us because once we consider the product AB and verify this equation for A and B in that order, we do not need to then again consider BA because of this abelianness. So that reduces our number of calculations somewhat. It halves the number of calculations. But still we can do something else also. Let me just keep the function intact. Also, something else can be noticed here. If say A is equal to 1 of these elements is say 1, the identity element in the group, then f of AB, what happens to f of AB in that case? If A is 1, then AB is just B, and the calculation of AB of course is carried out in U8. So this is just f of B. But now in the group U12, you can write in place of f of B 1 times f of B, because that one is the, just like this one is the identity element of U8, we also have the identity element of U12. But because of the definition of our function, f of 1 is equal to 1. So in place of 1, we can write f of 1, which is nothing but f of A. In other words, if at least one of these two elements is 1, then automatically our, it's verified. Our formula or whatever condition we want to verify, that is true. So we need not worry about 1. We have to look for the other possible products. Now we go through the calculations. So the first product that arises is 3. Do not forget that A and B can be equal also. So the first product is 3 times 3. 3 times 3 is 9, but in U8, 9 is equal to 1. So this is f of 1. But f of 1 is 1, so we have written 1 there. But 1 is also equal to 5 times 5 in U12, because in U12 ordinarily 5 times 5 is what? 25, but when we divide 25 by 12, the remainder is 1, and that remainder is of course our result, final result. So we have 5 times 5 here. but 5 is just f of 3. So that's how we have our equation when a and b are both 3. Then what about 3 times 5? So if we just simply carry out the calculations like this, then we get, it turns out that this is 7, which is, why is it 7? Because it's 15 and 15 is 8 plus 7, so that is why it is 7, okay. And f of 7 is what? F of 7 is 11. In U12, 11 is 5 times 7, which is just f of 3 times f of 5. Then 3 times 7. Note that because of this fact, we do not have to again see what happens to f of 7 times 3. So that's the advantage of having abelian groups. So this becomes 5 and f of 5 is 7. In U12, 7 is 5 times 11. And this is f of 3 times f of 7. So we have seen what happens when one of the factors is 3. Next 5. 5 times 5 is 1. That is because it's 25, and 25 is 3 times 8 plus 1. F of 5 is 7. And in U12, 7 times 7 is 49. 12, so yes, it will also be 1. So this is nothing but f of 5 times f of 5. Next, 5 times 7. 5 times 7 is 3. F of 3 is 5, and in place of 5 we can write 7 times 11. 7 is f of 5 and 11 is f of 7, and finally f of 7 times 7. Now this is going to be what? 1? Yes. 1, and 1 is also 11 times 11 in U12, because 11 times 11 is 121, and 121 is 12 times 10 plus 1. So that's it. We have completely verified this for all possible products. Here we have just simply gone through the ordinary calculation, and because of these facts, these symmetries, we have in fact essentially verified everything. Hence, F is an isomorphism of U8 onto U12. Thus, U8 is isomorphic to U12. So isomorphic groups are actually the same structure. There is no fundamental difference between two isomorphic groups. They are just presented or represented differently. Okay, that is you can see here. On one hand, you have the elements 1, 3, 5, 7. On the other hand, you have the elements 1, 5, 7, 11. Now it is like two worlds. Say there is a mirror. On this side of the mirror, you have one world in which something goes on. Whenever two elements interact, you get another element. Now when their mirror images interact, then also you get another element in the mirror world. The association is such that once you see what happens here, you will automatically know what will happen to the mirror, what the mirror images are going to give you. So they are just the same thing, just they have been written differently, that's all. And similar idea is there for other kinds of mathematical structures also. For example, between two topological spaces, you have the notion of a homeomorphism. Just like that, here you have the notion of an isomorphism. And with this, let us just end the video. In the next Gallian group update, we are going to solve the other exercises that come after this. And tomorrow, of course, as usual, we are going to do real analysis. So see you tomorrow with that. Until then, this is me, Lucifer, from a mathematical room. Have a nice night.